So chapter 7 is about thermochemistry. So this is energy in relationship to chemistry and chemical reactions. So the weather here is finally getting a little cooler, so we can at least imagine that in the winter, on those really, really coldest of days when it gets down to all of like 30 degrees Fahrenheit, you might need a hand warmer if you were outside for a long period of time, say watching a high school football game. So you can buy those little hand warmers, they sell them at 7-Eleven, and you open the package and you just kind of mush it around. It looks like it's got dirt inside of it, and it magically gets warm, right? It's not magic, it's chemistry. This is the chemical reaction that's occurring in that type of hand warmer. There are finely divided little pieces of iron react with oxygen and forms iron oxide. So really you're benefiting from iron rusting inside this little pouch. And that's why when you open the plastic, when you break that seal, it starts heating because oxygen gets in. So how much does that heat up your hand? Well, it depends on how big the hand warmer is. The bigger the hand warmer, the more heat you get. Depends on the size of your glove, right? If you have like really big gloves, you're not going to feel as much heat as if you have smaller gloves that are close to your hand. But mostly, the amount of heat that you feel depends on how much energy is released by the chemical reaction. So the universe is composed of matter, but also of energy. Because there are things that are not matter. Remember, matter has mass and takes up volume, takes up space. But then there are things like light and fire, right, that are not matter, and yet they are very real, and those are energy. And so even though in chemistry we're studying matter, energy affects matter. And energy is often the driving force that causes chemical reactions to happen. So chemists are interested in energy as well. So thermochemistry is the study of the relationships between chemistry and energy. Energy is the capacity to do work. Work is a force acting over a distance. So I take this beaker and I push it across the bench. I just did work. That's work. Heat is the flow of energy caused by a difference in temperature. So energy can be exchanged between objects through contact. If you're holding a hot cup of coffee, you feel the heat in your hand from the hot cup of coffee. It gets transferred. The thermal energy is transferred from the hot coffee into your hand. You put ice cubes in your rock star, right? And the rock star gets cold and the ice is getting warmer. Heat is being transferred from the warmer beverage into the colder ice. That's a heat, thermal transfer. You can also have kinetic energy being transferred when you hit something and you move it, or when you throw a ball, you are transferring energy to that object. So energy is a quantity. These terms can be very confusing. We have energy, heat, work, and it's kind of muddling what all of these things are. So think of energy as a quantity that an object can possess. So I think of energy as being a lot like money. You can have money, right? You can look in your bank account and you can say, I have $5.50 left for the rest of the month, right? But it's something that you can have. Heat and work are ways that the energy can be transferred from one thing to another. So if I give you $5, that's heat or work, that's a transfer of energy. Or, if I sell something to someone and they give me the money, right? Or I babysit their children and they give me money. That's the transfer of energy. So heat and work are ways that energy can be transferred or exchanged. So here we have an illustration with billiard balls, pool table, right? So here we have the cue ball. The white one is in motion, and this purple ball is just sitting there. So this cue ball has kinetic energy because it's moving, right? Kinetic energy is related to the mass of the object and how fast it's moving. So when it hits the purple ball, what happens? There's a transfer of energy. Now the purple ball is going to be moving. Depending on exactly how they hit, the white ball might also be moving, or sometimes it'll just stop and transfer all of its kinetic energy to the other ball. But this is an energy transfer. This energy transfer is not due to a temperature difference. This is work. It's a force acting on something else. So that's an energy transfer. So now the second ball has the kinetic energy that the first ball had. So energy can move into an object or out of it. Money can move into your wallet or out of it, right? Different types of energy. Kinetic energy is the energy of motion. So when things are moving, there's kinetic energy. Thermal energy is a type of kinetic energy. Thermal energy is the energy associated with temperature. Remember, temperature is the measure of the average kinetic energy of the particles. So we typically think of kinetic energy as like a ball rolling across the floor or a car driving down the road. It's moving through space, it's traveling over a distance. But kinetic energy is also wiggly energy, right? So I've said before, solid state of students, when you're sitting in chairs, are you moving? Yes, you are. You're shifting positions, you're scratching your head, you're breathing, you're taking notes, various things, right? All of that is movement. Are you traveling through space? No, but you're moving. And so that's sort of kinetic energy where there isn't traveling. That's thermal energy. So there's kinetic energy, energy of motion. Let's just highlight these. So there's two broad categories of energy. Kinetic energy and potential energy. So potential energy, like the name suggests, is the potential for something to happen, right? So this is energy that's stored in an object. And this can be associated with the composition of an object or with the position of an object. So here I have a Sharpie marker. Love these things. And if I hold this out, it has potential energy, because what's going to happen if I let go? It's going to fall. Does it have a lot of kinetic energy right now? No. What about if I do this? If I move it up and down? Now it's got kinetic energy, right? I'm really tired of doing that. So here it has very little kinetic energy, but when I let go of it, it starts moving. As it gets closer to the floor, its potential energy decreases, but its velocity increases. And so the potential energy is being transferred into kinetic energy. So that's an example of potential energy due to the position of an object. We can also have potential energy due to the composition, and we call this chemical energy. So the inside the substance, like perhaps gasoline, right? Gasoline has a lot of stored energy in it. It's got a lot of potential energy. If you ignite it, it will explode and release that energy into the surroundings. Well, why does gasoline do that? Water doesn't do that. It has to do with the relative positions of the nuclei and the electrons in the atoms that make up the gasoline. So it's potential energy due to position, but position on a very, very small scale. And so it's easier to think of that as being due to the composition of the substance. Some compounds are like compressed springs. They contain potential energy that can be released in a chemical reaction. Any questions yet? So this is a summary. You have energy is the capacity to do work. There's kinetic energy due to motion. A subcategory of that is thermal energy associated with temperature. Another category of energy is potential energy due to position or composition. As chemists, we're interested in chemical energy, which is associated with the positions of the electrons and the nuclei. So the law of conservation of energy states that energy can be neither created nor destroyed. So we can transfer energy from one object to another. We can change the form of energy, but we can't make new energy, and existing energy can't be destroyed. So here, this is like the demo I did with the marker. Here I have a picture of someone holding a ball above the pool table. Here it has gravitational potential energy due to its position elevated above a surface. And you drop that ball, and as it begins to fall, it gets closer and closer to the table, and the closer it is to the table, the less potential energy it has. But it also moves faster. So the potential energy is being transformed into kinetic energy. Does that make sense? Oops. If you press a spring, that's a type of potential energy. It's mechanical potential energy. So here this woman is pushing a ball down on a spring, and so she's storing energy in this spring, and when she releases the ball, this potential energy in the spring is transferred into kinetic energy and shoots the ball up into the air. So what chemists are interested in is the exchange of energy between something we're interested in and the surroundings. The universe is a big place, and so we can't look at everything all at once. And so what we do is we say, well, we're going to look at this particular thing. We call that the system. And we can define that however we want. And then the surroundings is everything that the system can exchange energy with. So technically, the surroundings is the rest of the universe. We don't always have to consider the whole universe, though, because sometimes the significant energy transfer is only going to happen within a small region of that universe. So the system, for our hand warmer example, would be the iron reacting with oxygen in the hand warmer. The surroundings, the area of the universe that has a significant impact, is significantly impacted by that system, would be your hand, the glove, the air inside the glove, even the air outside the glove, but just that local area is where the heat would be transferred. We wouldn't have to worry about temperature changes in San Francisco due to me opening a hand warmer in Fresno, right? Oops, wrong button. So conservation of energy means that if one thing loses energy, that energy has to be gained by something else. And so we're choosing to look at the surroundings, looking at the system and the surroundings. And so if we have energy transfer, and these are like a gas gauge on your car. And so this system has its energy tank half full. And the surroundings were at 1/4. When there's an energy is transferred from the system to the surroundings, we see that the system went down and the surroundings went up in energy, and the change is the same amount. One lost, the other gained. This is how money works too. If I give you $5, I lost $5, you gained $5. Is there more money than there was before? No, it's just who has it. It's just the movement of the money, right? So when you buy and sell things, money isn't created or destroyed. It's just transferred from one person to another. So the total amount of energy is constant, but it can be moved around. So of course we have to be able to measure energy. It's a quantity that can be measured. And we've seen this equation before. The kinetic energy of an object is 1/2 the mass times its velocity squared. So in the SI system of measurements, the base unit for mass is a kilogram, so kilogram. And velocity would be measured with a distance divided by time, so that would be meters per second. So if we have kilograms for the mass and meters per second for the volume that gets squared, bless you, we get 1 kilogram times meters squared per second squared. And so that unit gets used a lot, and so that was given a name. It's called the joule. So it's kind of a funny spelling, Joule. It's pronounced jewel, like a jewel in the king's crown or something. And the abbreviation is a capital J. Now, I'm telling you this definition, but we're really not going to need to use that very much. But if you've taken physics, you might have seen something like that. A joule is actually a relatively small unit. A 10-watt light bulb, which is not a very powerful light bulb, would use 36,000 joules in 1 hour. Yeah.
Why do you convert kilojoules to calories?
Why do we convert kilojoules to calories? Because calorie is a unit that has, in its definition, is more significant in chemistry. And so both units are used at different times. It's like, why do we have inches and centimeters? Yeah. So the joule is a metric unit, and so we can use the prefix kilo, any of the other prefixes as well. But a kilojoule is 1,000 joules, 10 to the 3 joules. So another unit of energy we'll encounter is the calorie. This was originally defined as the amount of energy needed to raise the temperature of 1 gram of water by 1 degree Celsius. Some of these definitions seem a little strange, but if you think back to doing science when there was no technology, people had to figure out a way to quantify stuff. And this was something that they could measure, right? It's like, well, I have 10 grams of water and the temperature went up 2 degrees. I can measure the mass and the temperature of the water, and I can use that to measure energy. And so it's really kind of neat if you think about it. So a calorie is just a different unit of energy, and the relationship between these is a calorie is equal to 4.184 joules. This is an exact conversion. It was made that way. So that's a calorie. So a calorie is about 4 times larger than a joule. And then we have the nutritional calorie, which is the calorie that we're more familiar with. You know, you look at the soda and it's like 260 calories in a serving or something. That's this calorie. This calorie has a capital C. The other calorie has a lowercase c. Well, that's not confusing at all. And the abbreviation for calorie is CAL. This is a lowercase c. This is a capital C. The size of that C is significant. The big C is the big calorie. It's actually 1,000 calories, right? So it's 1,000 calories or 1 kilocalorie. So we use the lowercase calorie when we're talking about scientific experiments. But if you look at food, you're going to see this capital C, nutritional calorie. So this could show up on an exam. It won't be on the exam next Monday, but on the next exam, the exam is typed, and so there are capital letters and there are lowercase letters, and we should be able to recognize the difference. There are some typos on exams occasionally, but if there's a capital C versus a lowercase c, that's intentional. Okay, that's not a typo. You can't just say, oh, well, they made a mistake. No, it's intentional, and so you have to pay attention to that, okay? There are other units for energy. PG&E uses a kilowatt hour. Because these other units are just too small. So here's some energy conversion factors. A kilowatt hour is 3.6 times 10 to the 6th joules. 3.6 million joules. Yeah.
Will we need to know that?
You do not need to know anything about the kilowatt hour. I will give you this relationship that a calorie is equal to 4.184 joules. Okay. You need to know that kilo means multiply it by 1,000, right? You need to know that the capital C calorie is the same as the kilocalorie. The nutritional calorie is 1,000 times bigger than a regular calorie. And this other table just gives us an idea of what these units represent. You can look at that. I'm not going to take lecture time for that.